Bob, would you introduce tonight's speaker for the Madison DX Club program?
Yes, well, it's a pleasure to welcome back tonight Frank Donovan, W3LPL. Most of us know who Frank is. He's a well-known contester, well-known DXer, has an incredible station, and he's done also a lot of work in helping us understand propagation. And tonight he's going to give us a very, very timely presentation on 6 meters. As we guessed, the solar cycle is coming into its decline, and what we can expect of sporadic E and TEP. So whenever you're ready, Fred, please go ahead. I mean, Frank, go ahead, please.
Okay, let's see if we can do the sharing. And now you should see my slide.
Yes.
Okay, good. Okay, well, it's a pleasure to be back again. And it certainly was a very timely invitation, given that it seems to be universally understood now that this solar cycle is beginning its slow decline. But the decline is really slow, and there are some really good days. I'll just divert from the normal 6 meter focus of this presentation. But 17 meters was open until after 2 a.m. I suspect it was open all night long, especially into Central Asia. And 15 meters and 17 meters were open again all day today, near as I could tell, especially to Central Asia. So even though we're in the decline of the solar cycle, there's still some really interesting propagation. It's a nice relief from some of the terrible propagation we've had over the last month with all of these geomagnetic storms and solar flares, coronal whole high-speed streams, and other things that made the bands pretty terrible for a lot of the last month. But today was really incredible, and let's hope it stays that way. So back to the program in 6 meters. So we all had lots of hopes about F2 propagation. And for the most part, we were disappointed. Last fall, during a few days of October and a few days in November, there was some pretty notable F2 propagation. Also some notable disappointments. I caught an opening to India, but there was such a massive pileup that I didn't manage to get through. It's one of the things about FT8, you don't, the strong signal isn't necessarily the ideal thing. It's being on a clear frequency, and you can't tell what's clear on the other end of the path. So it's kind of a crapshoot, and I was on the losing end of that crapshoot to India. And my neighbor said, well, my neighbor W3UR said, well, while you were trying to work that VU7, he worked in FR and something else in the Indian Ocean. So I missed the 2 or 3. Well, that's all right. There's still many more to work in the future. So, this happened to be my 6 meter beam. We're not going to talk much about antennas here. It's 50 feet high, which works really, really well. My neighbor W3UR has a 7-element beam at 60 feet, and it works every bit as well as this big antenna. So, one of the very important concepts about 6 meter propagation is a lot of us have a great deal of knowledge we've gained based upon our HF operations, but 6 meter propagation has almost nothing in common with all of what we've learned about HF propagation. So you really have to put that aside and rethink what's going on, because it's really very different. For those who would like to dive into further detail, the book on the right, published by the ARRL, is modestly priced and has a good deal of very readable content regarding propagation. The 100th anniversary handbook, and of course the newest one, the 101st, has a completely rewritten section on propagation. It's very, very detailed, but it's written for hams, written by people like myself with professional experience, but written for the ham audience. It's readable, but it's not casual reading, but it is readable. And also, of course, all of this knowledge about propagation ultimately leads us to apply that knowledge to improved antennas and more effective antennas. And the ARRL antenna book is just the obvious place to go for that knowledge. So, Sporadic E is back in the spotlight because unless you live in the southern tier of U.S. states, and even there at the southern part of the most southerly states, like around San Diego or around Yuma, Arizona, or in the very southern part of Texas, or the very southern part of Georgia, or even that's a little too far north, or the far southern part of Florida, if you want to work TEP or any other form of DX propagation that's available to us on 6 meters now, you're going to have to use Sporadic E. And Sporadic E has certain characteristics that demand certain kind of antennas in order to use that very effectively. Anybody that's been following the solar flux index, and I'll talk about that a little bit later, probably noticed in the last few days that it's really taken a deep dive. But there'll be some really good days too. There's a tremendous amount of daily variability, and inevitably we're going to get some really good days, although the solar flux index is down at pretty low numbers, low 100s, but 17 meters was open apparently all night last night. So the solar flux index is not the be all and end all of HF propagation. There's a lot going on that gives us a lot of enjoyment, especially on the HF bands. So this presentation focuses exclusively on 6 meter ES propagation from the 48 US states, but I'll also mention I'm going to talk quite a bit about TEP, so I should have updated this slide. A good deal of the presentation will talk about TEP. The southern hemisphere of the Earth, Argentina, New Zealand, South Africa, their sporadic E propagation is somewhat different than our sporadic E propagation, although it's similar in most respects. Unfortunately, that topic is beyond the time I have available, so I'm not going to get into that, but I'll just leave it as a fact that their sporadic E is somewhat different than ours. So there are a variety of forms of sporadic E. If us living in the mid-latitudes of the United States are used to a particular form that we experience, especially in June and July, but there are other types too. For hams that live very close to the equator, like our friends in Brazil, there's a form of E propagation called equatorial E that occurs just about every day throughout the year within about 600 miles of the magnetic equator. I'll describe what the magnetic equator is a little bit later. And then there's a very rare form of propagation. My only 6 meter QSOs with Alaska used this form of propagation. It's called auroral E. And this is not auroral backscatter that we get to experience during periods when the aurora is visible. Auroral E, it sounds very much like propagation on 20 meters on a good day. There's no trace of any auroral backscatter sounds. It's very clean. And I made several QSOs with Alaska. It was early in the morning, about 1 a.m. When this occurred, and the aurora was visible here that day. And I decided to stay up late and see if I got any luck, and I was rewarded. But that's the one and only time that I've ever been able to successfully use auroral sporadic E. And I'll just mention once again that auroral sporadic E has no relationship whatsoever to auroral backscatter, except that they often occur on the same day. But apart from that, the phenomenon is totally unrelated. So let's talk about the kind of sporadic E we experience most days in June and July. The elevation angle for propagation via sporadic E is almost always below 8 degrees. So when thinking about the height of a Yagi antenna, turns out 50 feet is a very effective height to produce radiation at 8 degrees and below. My neighbor has his Yagi at 60 feet, and it works every bit as good as mine. But if you go much higher than that, the null in the radiation pattern starts being in exactly the wrong angles.
In Los Angeles. After this, I'll go home tonight, eat dinner with my family, maybe go on a farm for a family. Are going about their normal.
Okay, somebody has their microphone not muted. Okay, thank you. So 50 feet is a very effective height, and there's a lot of ways to get a Yagi at 50 feet, and you don't have to have a monstrous Yagi. A 3 or 5 or 7 element Yagi works just fine. So of course we're DXers, so the very common sporadic E that gets us to a distance of maybe 1,200 miles is usually not a lot of interest to us, except maybe to work the occasional station in the Caribbean. And even at that, only the northern part of the Caribbean for many of us. So we rely upon long distance sporadic E. And that is widely believed to be caused by chordal hops, caused by irregularities in the sporadic E patches. And when this propagation is good, it can be really, really good. From here on the East Coast, we get the occasional day, much less often than in the middle of the country. But we do get the occasional day when there's just unbelievable propagation to Japan. And my neighbor W3UR made a QSO in Taiwan via this path, so it can be incredible. But it's still sporadic E, and it still requires antennas with radiation angle 8 degrees or below. So this is a little graphic that shows the short distance or one hop sporadic E. And it's present at one time or another almost every day from early June through at least the middle of July, and often later than that. So from Maryland, Cuba is about the end of the line for single hop sporadic E, and then for distances beyond that, we're reliant on at least 2 hop sporadic E or chordal hop. So this is an example of 2 hops, and this is perhaps more reliable than the chordal hop type, because the chordal hop sporadic E requires irregularities in the sporadic E patches that are just right so that the signal propagates, using this graphic as an example, from Maryland up to the sporadic E patch, and then with an irregularity in the patch for it to propagate then over to another patch without an intermediate ground reflection, and then on to, in this case, to California. So I suspect that a lot of the sporadic E at distances of 4,000 kilometers or less, a lot of that may be double hop rather than the more efficient chordal hop propagation. So of course, the big advantage of coronal hot propagation, and why it surely is the dominant mode on these really long distance sporadic E events that we experience, is that there's no lossy intermediate hop. It's all the propagation path is contained entirely in the ionosphere, except for the propagation up from the ground at one end, then back down to the ground at the other. And it's truly amazing to me how strong these signals can be on occasion, and how frustratingly impossible it is to predict these events. In our case, from the East Coast, we typically get these openings to Japan starting around 5 o'clock in the evening, and usually they last less than an hour, but there's the odd occasion when we get lucky and it lasts longer than that. And I've been able to work as many as a couple of dozen Japanese stations from here on the East Coast, and I know further west in the United States, some hams have worked more than that in a single evening. So what's going on with this sporadic E stuff? It is incredibly complex. And for those who would really like to get into the nuts and bolts, shown on this slide is a link, and I'll provide a copy of these slides so you don't need to scramble and write all this stuff down. But this is a very readable tutorial on how sporadic E works. And I'm not going to try to get into the detailed nuts and bolts of that when a much more comprehensive tutorial is available online. But it depends upon the occurrence of vertical wind shears in the E region of the ionosphere. And these vertical wind shears seem to be easily upset by other wind patterns in the E region. This is thought to be the reason why sporadic E is somewhat less reliable during solar maximum. And why is that? Well, the process of ionization in the E region creates heat. And of course, when you heat the atmosphere, even though the atmosphere in the E region is very thin, when you heat that region, it then creates wind patterns. And those wind patterns are thought to, this has not been proven, but are thought to upset these vertical wind shears, which then make sporadic E somewhat less reliable, because it's not very reliable at all, but less reliable than it is during solar minimum. So there's some thought that it's heating resulting from the ionization process that causes more reliable, especially long distance sporadic E during solar minimum, more reliable then than it is near solar max. And this thickness of the sporadic E patches is remarkably small, just a couple of kilometers thick in the vertical wind shear. And the elevation above the surface of the Earth is quite predictable. It's typically at about 100 to 110 kilometers altitude. And as a result, it's very easy to determine what the angles of radiation need to be. For those who operate HF, the height of the F2 region is highly variable, and it makes it difficult to determine analytically what the angle of radiation should be. And it's highly variable. But on the other hand, for sporadic E, we know that the reflecting layer is at a very predictable height. And with some spherical geometry, you can determine exactly what the angles need to be from your antenna. There's no guesswork involved. And there are all kinds of things going on here that affect sporadic E, and I've shown them in this little cartoon here. There are tides that compress the sporadic E layer coming from down below. There are atmospheric gravity waves coming from down below in the lower atmosphere. There are planetary waves and there are also traveling ionospheric disturbances, all of which contribute to the unpredictability of when sporadic should occur. And there are some repetition patterns that have been detected in 8, 12, 24, and 48-hour periods. And a lot of us have noticed that if we have a long-distance sporadic opening to Europe, for example, there's a pretty good chance it'll happen again on the next day. Not absolutely sure, but a pretty good chance you'll get 2 days in a row. But beyond that is very hard to predict. So I'm not going to try to explain this chart in detail. For those that are interested in this tutorial below, it has a lot more detail and more than I could cover in the short time that I have available with you folks. This is kind of an interesting graphic that came from the German Research Center for Geosciences. And what this shows is the altitude of a sporadic layer. And you can see that the most intense part of this layer is around 104 kilometers above the ground on the day when this was taken. But this is highly repeatable. And you can see how at dawn, the sporadic layer was just beginning to form, becoming more intense by 7 a.m., by 9 a.m., much more intense, by 10 a.m., reached its peak. But also its altitude was slowly dropping, but not by a lot, just by a few kilometers. And then by noon, it was starting to fade significantly, but then in the evening, the ionization came back again, but not as strong as it was early in the morning. Now, all of these times are local solar time at the location of the sporadic ionization patch. So it's not local time where you are. So if we're, let's say, beaming to Europe, it's a pretty good chance that this ionization patch is one time zone to our east. And if we're beaming to Japan, pretty good chance that the ionization patch that we're entering into is perhaps one time zone to the west. So unfortunately, the sporadic season starts to decline pretty significantly after about mid-July. So if you're interested in using sporadic for DXing, you've kind of got about 5 weeks from now, and then the propagation becomes less reliable. It's not to say we can't have the occasional really good day. We can, but it's not very likely. It's much more likely between now and about the middle of July. So what's going on here? The cause of ionization for sporadic has absolutely nothing to do with the ionization process that affects HF propagation. In the HF bands, the source of propagation of ionization is radiation from active regions on the sun. We used to call them sunspot regions, but the more commonly used term to describe those regions now is active regions, because they contain other things other than sunspots. Also, they are the source for coronal mass ejections and solar flares. So the commonly used term is active regions, but it's the same thing we used to call sunspot regions. So sporadic ionization has absolutely nothing to do with that. It's all about Meteor penetration into the atmosphere. And of course, many of you have probably seen shooting stars. If you haven't seen them, you've probably seen YouTube videos of them. So when meteors, and more accurately, micrometeorites, very, very tiny ones, when they enter the atmosphere, when they get down to the layer of where sporadic forms, that's where the energy is released from the extreme high temperatures when those meteors get down to the E layer. And that's what causes the ionization. It has nothing to do with the sun, unrelated. It has to do with the entry of these micrometeorites into the Earth's atmosphere. And you can see here in this chart that the average daily count of meteors peaks from the middle of May until the middle of August, and then it drops down quite low from August through late April, early May. So one very important attribute of this kind of ionization is that it's very long lasting. Unlike the ionization of mostly oxygen atoms in the F2 region that affect HF propagation, that ionization is much shorter lived. And in the E region, where the atmosphere is more dense than at the F2 region, the ionization process in the E region, the ionization process from the sun, is very short-lived because the atmosphere is significantly more dense at the E region elevation than it is at the F2 region. So in the F2 region, which we use for HF long-distance propagation almost exclusively, of course, there's no source of ionization during the night, but that ionization persists throughout the night just because the atmosphere is extremely low density. So it takes a long time for those electrons to recombine at the F2 region. But at the E region, those electrons recombine almost instantly once sunset occurs. But if it's sporadic E, the source of ionization was these heavy metallic ions, the heavy metals that were ionized as they entered the Earth. And that ionization lasts for a very long time. It can last for as long as 24 hours, more likely less than that, but nonetheless, very long period of time. And that is one of the key attributes of sporadic E, is the long life of ionization. I'm sure many of you have noticed that when we get a really good sporadic E set of openings, these openings can last for hours. We had a really good day here on the East Coast, and I suspect it went as far as the Midwest into Europe last week. And that opening lasted for more than 4 hours and lasted into the early evening. So this is all interesting theory. So, but what are the practical aspects of this in terms of how do we take advantage of these unique characteristics of sporadic E in the design of very effective stations for DXing? Well, one is that this sporadic E propagation is highly spotlighted. Typically, the east-west width of the ionization patch is anything from 50 to 300 miles. And it's rarely an extent more than 50 miles north and south. So if you call your friend 100 miles north of you and tell him about this fantastic opening of long-distance sporadic E, there's a very good chance that someone 100 miles north or south of you will get no trace of it. On the other hand, someone 100 miles east or west of you has a better chance. Not guaranteed, but a better chance than someone at that distance north and south. For sporadic E propagation, the MUFs exceed 50 megahertz every day during June and at least through the middle of July. And in fact, through many days in July, but not necessarily every day, but not necessarily everywhere. So you have to be in the right place, and this is what we often call spotlight propagation, where someone 2 or 3 states away from you might be having a fantastic day, and all you're hearing is just the ordinary noise. And this long distance propagation that we rely on as DXers occurs during many days from early June. And I've had a couple of really interesting DX experiences during the last couple of days in May. Those are very rare though. But from early June through mid-July, and a few days in late May, and a few days in early August, and there's even a few days in late December and January. But boy, you've really got to be patient to catch those days. But from now to mid-July, the opportunities are a whole lot better than they are at other times of the year. To the best of my knowledge, and for all of my experience, the propagation path is true great circle. I have personally never experienced a sporadic that was skewed off of the direct azimuth. I wouldn't be surprised if it has occasionally happened, but I've just never experienced it. By far, the preferred antenna is a horizontally polarized Yagi. For the odd situation where it's not practical to put up a Yagi, you definitely want to have horizontal polarization. And the reason for that is the efficiency of the ground gain for vertical polarization is very poor. So on 6 meters, no matter what, you want your antenna to be horizontally polarized. Doesn't mean you can't work the occasional DX with vertical polarization, but you're really handicapping yourself very badly. Optimum heights are 50 to 60 feet. That doesn't mean an antenna at 30 feet won't work. It's just a handicap. And similarly, if you go above 70 feet, then the first null in the radiation pattern of the antenna is right at the angles where you most want to have maximum gain from your antenna. So if you're a 6 meter DXer, it's all right to have a very high antenna, but you better have one at 70 feet or below, or you really will suffer. Now, for those that can't put up antennas at 50 feet or so, a 25-foot height is only about 3 dB worse for shorter distance sporadic E, but for distances beyond 2,000 kilometers, it's about 6 dB worse at a height of 25 feet. So it's really important to try to get up to about 50 feet if you can. And the other thing that affects 6 meter propagation is if the antenna is sitting in a densely crowded area, whether that's a dense housing development or dense forests within about 1,500 feet of the antenna. And you really would like to be up above that clutter if it's possible. So here's some of the easily observable extreme variabilities of mid-latitude sporadic E occurrence rates. Sporadic E occurs on essentially every day during June and July, but not necessarily everywhere and every day. So you inevitably will experience some days when 6 meters appears to be totally dead. Well, it probably is where you are, but 300 miles north of you might be a whole different experience. Although most of the sporadic is over with by the end of July, there's still the occasional day in early August when we might get a brief opening, but you really need to be patient to catch those. And then we get some really interesting sporadic E starting in mid-December through early January that can give us openings into the South Pacific. And at this part of the solar cycle, those openings continue even to now. but we still need, most of us still need that one, at least one hop of sporadic E in order to get into some of this other propagation. And I'll be talking about that in just a few moments when we get into TEP. Some of this propagation, sporadic E propagation, can last after midnight, especially the one hop sporadic E. But some of these stations that we work in the Pacific, it's around midnight or later when we're working them from the United States. And the variability, of course, sometimes we might experience sporadic E propagation, and a few seconds later it's gone and doesn't return. So we just get teased. But most of the time the propagation lasts at least a few minutes, and in many cases, like last week, it lasts for hours. Now these sporadic E clouds don't stay in the same place; they gradually drift. So the most common drift is south to north along magnetic field lines. So if you know where the magnetic field lines are in your part of the United States, then that drift tends to follow those lines roughly south to north. And I think I've discussed all these other topics. There's extreme day-to-day variability. About the only correlation I've ever been able to perceive is that there's a pretty good chance, if you have really good propagation on one day, that the next day there's a better than average chance that you'll get another good day. But apart from that, it appears to be highly random. So with regard to F2 propagation, the transatlantic and transpacific F2 propagation that we enjoyed last fall, it appears to be done with. So what we're left with is TEP propagation, and it's still pretty good, but it requires a sporadic E hop. So a lot of these characteristics of sporadic E are very important for us to be able to couple into a TEP opening. And, we might hear some of our friends down in San Diego or extreme South Texas or south of Miami working TEP, and we can't work it at all because we don't have a sporadic E hop. And the rest of this is TEP. So for those of us who've been working these relatively frequent TEP openings over the last 2 or 3 years, what's going on there is that TEP, transequatorial propagation, is actually an enhanced F2 propagation. And I'll show you the mechanism in just a moment. So the basic propagation mechanism is caused by ionizing radiation from the sun, unlike sporadic E. So TEP, that ionization comes from the sun, but it's enhanced by a kind of an amazing process that I'll describe briefly in just a moment. So we expect to see these frequent TEP openings into South America, or what's called oblique TEP into Africa. For example, D2UY has been quite active. And a lot of us have worked him over the last couple month or two. And also the TEP openings we get into FO and the Cook Islands, New Zealand, and occasionally, but pretty rare, into Australia, particularly the VK4 area, which is closer to the equator. So we've got probably another year, and maybe if we're lucky, maybe 2 years, when we'll really get to enjoy some of this TEP openings that we've had for the last few years and some of the DX that it makes possible. So let's take a look at the sunspot cycle. So this graphic comes from one of my favorite websites regarding the solar cycle, and that is the NASA Marshall Space Flight Center. And this is the URL for their forecasts, which they update on about the 10th of each month. And they have an interesting approach. They don't produce, when they produce this graphic, the 50th percentile, shown in green, is the most likely forecast outcome. But then they forecast a very, very pessimistic forecast, shown in red, the 5th percentile one. Well, we already know that's not true. I don't know why they still publish that one. And then there's a more optimistic forecast called the 75th percentile. And you notice it's pretty close to their 50th percentile in green. So there's not much variation there. And then there's an extremely optimistic forecast shown in blue. And you can see that forecast suggests that the solar cycle is going to continue at about its current level through 2026. Well, we can see that's not happening. So this very optimistic forecast is just not real. So we're somewhere between the green and the purple lines, both of which are really close together. For those of us who operate 10 meters, solar flux index around 160 is what's needed for very reliable 10-meter propagation from September through April. Unfortunately, for 6 meters, we need solar flux units well above 200 in order to get reliable F2 propagation. And we had very, very little of that last year. And just a few days of really good F2 during late October, early November last year, and then it was done with for this solar cycle. So many of you have probably heard that the sunspot cycle occurs somewhat differently in the northern hemisphere of the sun compared to the southern hemisphere of the sun. And this graphic illustrates that. The sunspot number, total sunspot number, is shown in blue. So we reached an international sunspot number of about 160, smooth number, total sunspot number. But notice that the southern hemisphere, shown in purple, was much, much more active last year, made a much bigger contribution to the peak of the sunspot cycle than the southern hemisphere, shown in the light blue color. More than twice as much ionizing radiation came from the northern hemisphere compared to the southern one. And notice the peak of the activity from the southern hemisphere appears to have occurred in 2023, about 2 years ago, and there's no indication at all that that we're going to see another peak from the southern hemisphere. So it's almost certain that the solar maximum occurred last year, sometime between July and October. This is kind of another way to look at sunspot cycles. This very messy graphic shows the progress of every solar cycle since the beginning, so for 100 years. And the ones that are highlighted are the ones since the big solar cycle in 1958. And there's a couple of things that are interesting to notice here. And that is, if you look, for example, at solar cycle 19 that peaked in 1958, notice how it rose very rapidly from solar minimum. It reached solar maximum about 3.5 years after the minimum occurred. But if you look at the current solar cycle 25, which apparently reached solar maximum last year, notice it rose much more slowly. And if you look at the very weak solar cycles below that, especially solar cycle 24, that peaked 11 years ago, notice how they climbed even slower. So here we are, we're now actually 66 months, I believe, after solar minimum. And notice now, if you look at all of those solar cycles, all 25 solar cycles after you get to month 65, without exception, they're all in decline. No exception. That doesn't mean over thousands of sunspot cycles, there haven't been exceptions, but over our lifetimes, there have been no exceptions. They're all in decline by the time the 65th month. Another interesting way to look at this sunspot cycle, the image on the right is a combined image of all the sunspots during the year 2024, apparently the year of solar maximum. And notice all the bigger sunspots are in the northern hemisphere. And there are quite a few tiny sunspots in the southern hemisphere, but almost all the bigger ones were in the northern part, above the equator on the sun. And the graphic on the left side shows the contribution to the sunspot number of the northern and southern hemisphere, and I think this is backwards. I just noticed now that this is appears to be backwards. But anyway, I'll have to go back and take a look at this and figure out what's going on here. But what you can see from that graphic on the left is that one of the hemispheres was much more active than the opposite one. Let me go back again here. Yeah, and I'm sorry, I just got a little bit confused. So if we look at this chart, you can see the southern hemisphere was much more active than the north. So the purple was much more active than the north. And if we look at this graphic, it's exactly the same. So the south was much more active, it's shown in red, and the green in north. There was a little bit of some hope in January when the northern hemisphere got to be a little more active, but it was disappointing. It settled right back down again, and it really hasn't peaked since. So here's a more detailed forecast for this solar cycle. It's available on the SWPC website, where a lot of us go for solar information. And this shows the progress of solar cycle 25 right up until today. So just looking at the notes on this graphic, starting in December 2022, that was when this sunspot cycle really started to show some energy. So that was only 2.5 years ago when we really started to see a pickup, and this sunspot cycle reached a local maximum, a short-term monthly maximum, in August of 2024. And you notice it's settled down since then. And the forecast on the SWPC website shows a steady decline of the solar cycle from where we are now in 2025, and a steady decline below a sunspot number of 100 by the end of 2026. And after the sunspot number gets below 100, we'll start to notice much less frequent TEP on 6 meters. So we've probably got another year, maybe 2, of some pretty interesting TEP propagation to South America and occasionally to Africa and the South Pacific. But after about the end of 2026, it'll be much less frequent. Now, along with the benefits of ionizing radiation from the sun, also comes more frequent geomagnetic storms. And anybody active on the HF bands during late May and the very early part of June experienced some pretty terrible propagation. And what's going on here is that geomagnetic disturbances caused by particle radiation from the sun become much more frequent after solar maximum. This forecast is from the Marshall Space Flight Center, the same one that does the forecast of the sunspot cycle. And what this and they do it kind of the same way. The green line is what they believe to be the most likely forecast, most likely to be correct. And then they produce a pessimistic one, which suggests that geomagnetic disturbances and disturbed propagation in general will become less frequent. Well, that's opposite for what's happening. We're starting to see a lot more disturbed days now. So the red line is not relevant. We seem to be seeing something more like the green line, but they also produce a very optimistic forecast in terms of disturbances. And I hope this doesn't happen. There's no evidence that it's going to, but it shows much more intense disturbances lasting through 2028. But I'm counting on this 50% green line to be the more likely outcome, which suggests that we're going to see frequent disturbed propagation from now through the next couple of years, and then it'll start to settle down again as we approach solar minimum about 6 years from now. This is a very complicated chart, but it has a kind of a simple message. But you need all this complexity to show it. So near solar minimum, most of the disturbances of particle radiation from the sun comes from something called coronal hole high-speed streams. You can see, of course, those 4 pie charts across the top of the screen, the CHSS effects, coronal hole high-speed stream effects, cause the vast majority of geomagnetic storms near solar minimum. Conversely, if you look at the bottom half of the slide, the vast majority of geomagnetic storms of all sizes near solar maximum, and we're certainly near solar maximum right now, are caused by coronal mass ejections. Those are associated with active regions on the sun, and those active regions become much less prevalent on the surface of the sun after we get a few years beyond solar maximum. So 2 very different causes. The CMEs produce much more severe disturbances than coronal holes. Coronal holes are usually associated with minor geomagnetic storms. Operative word is usually, occasionally it's stronger than that. Whereas the CMEs are very often associated with very severe geomagnetic disturbances like we had a couple of weeks ago. And that was kind of amazing a couple of weeks ago where this badly disturbed HF propagation lasted for nearly a week. Very unusual. So let's take a look at TEP propagation. As I mentioned, TEP is F2 propagation. It's not a unique form of propagation at all. It's F2, but it's enhanced, and I'll show the enhancement mechanism in a moment. There's also TEP propagation if you happen to be on a de-expedition to the Caribbean. The enhancement is just incredible. I was in Curacao many years ago and experienced this, and I also experienced it in Hawaii. Just incredible how frequent TEP propagation is when you get closer to the equator. A whole lot different than the experience we have here in the US. There's a particularly good article about F2 transatlantic equatorial propagation that's available on the web, and the website is shown. And as I mentioned, I'll provide a copy of these slides so you can get access to this. It's a very readable article by a well-known propagation expert for 6-meter propagation. His name is Jim Kennedy, K6MIO, and this is one of his very best articles. So what is going on here with transequatorial propagation? It's an incredible process. And Jim's article describes it really well, the article from that I showed on the previous page. But what happens is in the E region, for us, mostly over Western Brazil, a process takes place that causes what's referred to as a plasma fountain, where there's an upwelling of ionization that is ultimately overcome by gravity, and then the effects of the plasma fountain come back down to the Earth, and they come back down to the Earth about 15 degrees latitude north and south of the geomagnetic equator. The geomagnetic equator sits over Western Brazil, so these ionization crests for TEP, for north-south propagation, they sit over Venezuela and Bolivia. And I'm sure many of you who've worked TEP noticed how incredibly reliable this propagation is into Buenos Aires. It's at just the right distance from these ionization crests that it seems like you can hear a pin drop in Buenos Aires some days. And in the Northern Hemisphere, and this is why operation from the Caribbean is so good, Haiti is at just the right distance. Haiti and Puerto Rico and Cuba and certain parts of Central America are at just the right distance from the ionization crest that they get this TEP propagation very, very often. And of course, they don't have to rely upon sporadic E in order to couple into it like we do here in almost all of the United States. The physical process that causes this upwelling of ionization from the geomagnetic equator is called the equatorial electrojet. It's on the day side of the Earth at the geomagnetic dip equator. Now, the geomagnetic dip equator, that's a kind of a fancy name. What that means is where the magnetic field in the ionosphere, not on the Earth, the magnetic field of the Earth passing through the ionosphere, where it is exactly parallel to the Earth, not tilted at all. And shown in this graphic is where the magnetic dip equator occurs. So you can see in the Western Hemisphere, it's over Brazil and extends out over Peru before it goes out into the Pacific. And one notable attribute of the geomagnetic dip equator, and it's a fortunate thing for us in North America, is that it's tilted quite a bit. Notice it's not true east-west as it courses South America. And this is why we get this greatly enhanced TEP propagation into Buenos Aires, where there's a lot of population and in just the right spot for this kind of propagation. And it's also why TEP into the South Pacific is less common. And I'm not going to read through this. You can read through this later, or you can read Jim Kennedy's excellent description. But the other significant thing about this is that the peak intensity of ionization for TEP at the point where the propagation crosses is roughly from 11 a.m. to 1 p.m. local solar time. But the TEP lasts well into the evening and many occasions. And this graphic kind of shows where the hotspots are for TEP. So in the thin line where it crosses Brazil shows the approximate location of the magnetic dip equator, where the magnetic field of the Earth in the ionosphere is parallel to the surface of the Earth. And then the broader black bands show the approximate location of these ionization crests, called the northern F2 equatorial ionization crest and the southern F2 equatorial ionization crest. And then at the very bottom of the chart, you can see how the most frequent propagation that we get via TEP is into Argentina, Uruguay, Chile, and the southern part of Brazil and Paraguay. And VP8 is just outside the sweet spot. So it's kind of similar to the situation we have in the mainland United States. So often propagation into VP8 will require a sporadic E-hop. Often, but not always. Sometimes they get lucky and they get direct access to TEP like the folks in Florida do. And this was a particularly good day. This is a PSK reporter. And just look at all of this TEP propagation. I don't remember which day this was, but there's a couple of interesting things you can see here. You can see that not only was there a tremendous amount of TEP propagation, especially from the southern tier of US states, but at the same time, the Europeans were enjoying this same opening. Their propagation courses a whole lot further east than ours does. And you'll also notice that there's a few spots where there was propagation very, very close to the equator. And that does happen very frequently. Normally, you would think if it were pure TEP, that the propagation would be into the southern part of South America. But what actually happens, and I'll just go back a couple of slides to speak about this a little more clearly. In fact, I can use this slide. It's not unusual for signals to propagate up to the northern equatorial ionization crest, up over Ecuador and Venezuela, and then for the signal to come back down to the surface of the Earth. So we can work via just the northern equatorial crest. We can work stations in the central part of Brazil or in Peru. We don't necessarily propagate only via both crests. We can propagate from the United States via only the northern crest as well. And this is an example of some of the propagation we get into the South Pacific. And shown here are the northern and southern equatorial ionization crests. And the magic from the east coast of the United States is if we can hear stations in Mexico or Texas, that's a good time for us to be looking for the possibility of propagation down into the South Pacific. And you can see the paths here. So it's sporadic E from the middle part of the United States, and then TEP, of course, the two crests. And then for most stations to Samoa, they're within the reach of the TEP zone, but New Zealand needs, especially the southern part of New Zealand, needs a sporadic E-hop just like we do. And this graphic shows what I just mentioned before about the possibility of working into Ecuador, Peru, Brazil, and Suriname via only the northern equatorial crest rather than true TEP. And D2UY is a very active 6-meter operator, and that is not true TEP because you can notice that the southern equatorial ionization crest is south of his location. He's located where the white dot is, and you might say, well, what's going on here? That's, you can see on this map, Angola is south of that white dot. Well, there's an enclave of Angola, and that white dot is in that enclave, and that's where D2UY is located. So that's propagation via sporadic E, coupling into the northern F2 ionization crest, and then down to D2UY. And he has pretty reliable propagation on 6 meters. And this is my approach to propagation, although it's interesting to understand all of these complex mechanisms. I really prefer nowcasting. And PSK Reporter, especially on 6 meters, is the very best one. This happens to be a snapshot of 20-meter propagation, but you can really see what's going on with 6-meter propagation by using a PSK Reporter. You can set it up to report only 6-meter propagation, and you can really get an idea what's going on right now. Okay, so that's the end of my presentation. I guess I took a couple of minutes longer than planned. I'll be happy to address any questions any of you might have.
Frank, that was a great presentation. What questions do we have for Frank?
Hey, Frank, this is Walt, Alpha Juliet 6 Tango. Could you again say why there's some indication of an understanding of why sporadic E is worse during the high times of the sunspot cycle?
Sure. No. Hello, Walt, and thanks for that question. You know, that's a very important one. And all I can say is this has not been proven, but the explanation that I've read does make some sense. So in the E region of the ionosphere, there's a lot of ionization going on there from the sun. Now that ionization of the E region is what causes 40 meters to be open in the middle of the day. So we all know if you get on 40 meters, you can use the E region to communicate from your location to a location, let's say 400 or 600 miles away. And that's ionization of the E region, not sporadic E ionization, but ordinary ionospheric ionization. That process of ionization creates heat. As the electrons are spun off from mostly oxygen atoms, it's a heating process. And that area of the ionosphere gets to be much hotter during solar maximum. There's a lot more ionizing energy coming from the sun. So that makes the E region hotter than it is during solar minimum. Well, just like any other place in the atmosphere, even at those very high altitudes, when you have heat gradients, it creates wind. And that wind upsets the vertical ionization. Let me just find that chart here. It's not too far back. I can describe it a little better from that chart. Oops. Further back than I thought. You'll be able to find it. Not too much trouble. That illustration makes it a little clearer. Yeah, here it is. Okay, so if you look right here, you can see these wind shears, and that's what creates these sporadic patches. And during the years near solar maximum, there's also quite a bit of wind moving perpendicular to those wind shears that is thought to upset those wind shears, making sporadic somewhat less reliable, especially long distance sporadic where we need multiple ionization patches, not just one, but we need an ionization patch 600 miles from us, and then we need another one, another 1,200 miles beyond that, and another one, another 1,200 miles further down, and then the probabilities of having these patches appear simultaneously is reduced because of these unwanted winds caused by the heating in the E region. Complicated answer, but it's a complicated topic, and it's all theoretical. None of this has been proven. Okay? Walt, your microphone is muted.
Yeah, thanks, Frank. That certainly has been my observation. There's less long distance really good double hop and European skip at the peaks of the solar cycle.
Right, but we had a great one last week. So all of this stuff is probabilistic. Yeah, it's less frequent, and we're pretty close to solar max right now. But we had a really great day last week. So it's all probabilities. But I agree with you completely. I've operated during several solar cycles, and solar minimum is a lot more friendly for DXers. When we used to have quite reliable sporadic propagation from the East Coast into the Persian Gulf, at least 2 or 3 times a year. And we had much more reliable propagation from the East Coast to Japan, nowhere near as reliable as you get. But that's much less frequent at this part of the sunspot cycle. But it should get a lot better as the next few years go by. Okay, any other questions?
This is November 4 Yankee Echo.
Yes, go ahead. What is your name?
Name is John.
Hi, John. Go ahead.
Hello. I'm located in Naples, Florida, and I just want to contribute what my experience has been over just the last 6 months since I installed an east-west dipole about 20 feet up in my attic. So the radiation is mostly north and south, and I've actually made about 150 contacts on 6 meters. Mostly in South America and the Southeast U.S. and a little bit of the Caribbean, but I've had fun with just that dipole.
Oh yeah, it's called the magic band for a reason. It's just incredible what simple antennas will do. Never say never. I've had my knuckles wrapped more than once when I've made some pessimistic forecast about what might happen on 6. And had to apologize for my pessimism. It's the magic band, and almost anything can happen. This propagation that we enjoy on this band shouldn't happen at all, but it does, and it's a lot of fun. Imagine what you could do, John, if you had a 3-element beam up at 40 feet.
Absolutely. There's an issue called HOA rules, but
Oh yeah.
totally agree.
Yep. But you've done the right thing by putting a horizontal dipole up there and not a vertical on your roof. I think you'd be very disappointed if you had a vertical.
Yeah, he's probably on. I've got a friend in Vermont, and he's just got verticals. I told him he should put a dipole in his attic for 6.
Yep. That's the right thing to do. Any other questions?
Frank, this is Lance, W7GJ.
Well, hello, Lance.
Hi. Hey,
So when do you leave on your trip?
I leave August 3rd, but it takes me 4 days to get to H40, so
That's going
I
to be
won't
an
land
adventure.
there until August 7th, and I'm, fingers crossed, hopefully by the 8th or 9th, I'll have everything set up and the palm trees cut down and be set up.
Yeah, and a big thank you for that TEP QSO that we had from ZD9. That must have been one of your very last QSOs on that trip.
Yeah, I only had a couple of good TEP openings to North America, so I was looking all the time when when I wasn't pointed at the moon, I was pointed at North America. So much to the chagrin of the Italians, but
they got over it, I'm sure.
My question to you is, from up here, I'm in the Pacific Northwest. I mean, I'm so far from TEP that it very rarely happens, although I'm surprised at the amount of times that I can work into Chile and Argentina from here. I think a lot of it's because I have a negative horizon that direction, so I don't require a whole lot of MUF to get down there. But what I'm asking you is if you have seen some mechanism along geomagnetic field lines, because I see oftentimes from the East Coast, the propagation to Europe is along geomagnetic field lines. From here to Japan during E-skip season is along geomagnetic field lines. But trying to cross those lines, you don't get that skip, 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 skip chordal hopping. And so from here, like to the Caribbean, I have to cross it. I have to get what I call hard E-skip skips. You know, it has to be an MUF of 50 megahertz at 3 places for me to get to the Eastern Caribbean.
Yep.
But, you know, the people that are further south, I mean, they're like in Southern California, they've got direct geomagnetic field lines to Europe. And they frequently get, you know, openings to Europe. Have you ever run across explanations for how the ionization kind of hangs along geomagnetic field lines or something?
No, I have not. You know, there's a you can find speculation to match just about any outcome you want.
Yeah.
And the sad thing is there isn't a whole lot of real reliable research that goes into this sort of thing. The research community doesn't seem to be very interested in this magic propagation that we enjoy. So about the very best and believable articles you'd find are like from Jim Kennedy, K6MIO. And that one article I pointed to was one of his very best. But that's about the extent of the research that we've got available to us. Apart from that, the best we have is our own experiences.
Mm-hmm.
We get to experience this, and just like you described, we kind of get to know what's most likely to happen, just from our experience. But you don't find a lot of scientific basis for this other than what Jim Kennedy wrote and a very few other authors.
Yeah, most of Jim's experience has been from the TEP zone. So,
That's right, from Hawaii. That's
those
right.
of us way far from it are, of course, all my de-expeditions, or most of them, have been close to the TEB zone or in it. So, it's a way different experience than being up here in Montana. But
Oh yeah, but difficult for EME sometimes also.
yeah, absolutely. It can trap the signals or block them or scatter them out of the way.
Yep.
6 meters is a tragic band for EME, but for many cases, it's about the only way you can work halfway around the world. So
Oh yeah, yeah.
I'll look for you during your moonset.
Well, I'm not active on EME, unfortunately. I did make a few QSOs, but I'm involved in a lot of things in ham radio, and I decided that one was likely to take more time than I could devote to it. So at least for the moment, I don't have any capability.
Well, I'm going to devote 3 weeks to being down there. So please beam west during your moonset and watch for me.
I'll do that, but
I worked a lot of single Yagi stations from ZD9.
yeah. Yeah, and as you saw in that opening slide, I've got a big single Yagi, but it's strictly at the horizon.
Yep, that's fine. You
Yeah.
need the ground gain with a single Yagi, so that'll work.
Unfortunately, when I will be pointing at you, I'll be pointing right through my house.
Oh, that's not good.
That's not good. That's right. Full of metal. Yeah.
Well, good luck and thanks, Frank.
Okay. Then thanks for everything you do, Lance. It makes us all smile. Any others?
Hi, this is KA2CGB, Brian.
Hello, Brian.
I believe I understood you to say, and if that's correct, I'd like you to perhaps refresh my memory on how that when, for example, a KP is elevated, we tend to have some enhanced propagation.
Yeah, so it's a very complex topic. but when the KP is elevated, it forces some migration of ionization, and of course it's the electrons that cause ionospheric propagation, and they're confined to moving along magnetic field lines. It's absolutely impossible for them to move any other way. So when the KP index is somewhat elevated, not a big geomagnetic storm, but somewhat elevated, it's not unusual for those electrons to drift along magnetic field lines southward, and it can enhance the MUF further south. And even when we get a really severe geomagnetic storm, there's a possibility of some big enhancement on the TEP path. But your observation is exactly correct. Mild disturbances of the K index can produce a higher density of electrons, particularly as we move to more southern latitudes. And this may be related somewhat to Lance's question, where there's a tendency for the electrons to drift along magnetic field lines. They can't drift any other way. They are absolutely bound to the geomagnetic field lines, and it's not unusual when the K index is elevated a little bit for the MUFs to be somewhat higher at the more southerly mid latitudes than they are at the more northerly mid latitudes, like where Lance lives.
Really good. Thanks a lot. I really enjoyed the presentation.
You're welcome. It's an incredibly complex topic. You know, I probably discussed a dozen topics, and you could obtain a PhD in any one of those topics. And we covered each one in about 10 minutes.
Frank, I'll just add a comment that anecdotally, I've only been on 6 meters for 20 years, but it seems like after a big spike in KP, when it's moving back down again off of 5 or 6 or higher and starting to tail off to like 3, that's our typical time for us to get good E-skip to the south. And finally, then often we'll be able to connect to TEP, or I'll have double hop E-skip to the south and be able to connect with TEP. So it's
I guess you need double hop to get down to the TEP zone.
Usually, yeah.
Yeah. Usually indicated we often use in Maryland and a lot of other mid latitude, more mid latitude than yours, is when we start to hear stations in Florida, Cuba, Puerto Rico, then we might be in for some really good TEP propagation. Okay, any other questions?
Frank, this is Jose. I just want to make.
Yeah, I'm sorry, whoever that was, I didn't get what you were asking.
No, I'm just said what I was. This is why I just want to make. I'm a newcomer to 6 meters, and so far I've only been able to have USOs with Chile, Argentina, and south of Brazil. Can I expect to make any uses with other regions, or is it due to my location?
And who is this? I missed who you are.
This is Yankee Sugar 1, Mike Sugar.
Oh, okay. Jose. Yeah, thanks for that question. Well, I think you're going to see a lot more sporadic E over the next 6 weeks. So a lot more than you've seen up until now. So I think there's some real opportunity for you to work into the more northerly regions of North America over the next 6 weeks. The propagation you described was probably TEP propagation, transequatorial, that I described. And TEP is really, really good from your location, especially down into Argentina.
Okay, then I'll just keep my radius on more time than
yeah, especially in the afternoon.
Okay, thank you very much.
Okay, good luck, Jose.
Thanks.
Any other questions for Frank? Well, this was, as always, Frank, we really appreciate these propagation discussions. And as Bob said in introducing it, it's very, very timely. There's a lot of technical matter. We'll put on our website your PowerPoint presentation, and we'll have the YouTube program up in a few days.
Good. So who should I send the PDF of my presentation to?
You can send it to Bob. He'll get it.
Okay, good. Yeah, because it has to be a PDF, otherwise the size is just crazy.
Yeah, no, that's perfect.
Okay, I'll do that in the next day.
All right.
Thanks, everybody, for attending,
Thanks, Frank.
and best of luck with the sporadic season over the next 6 weeks.
Thanks, Frank.
Thanks, Frank.
Thank you, Frank. Thank you, everybody. 73 is from Guatemala.
This is really great. Thanks all.
Thank you, Frank. Hope to copy any of you from El Salvador, 73.
I'll be looking for you.